Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue talking about sedimentary environments and sedimentary rocks. So in this video we're going to think about changes in the environment and how that leads to different sediments appearing within a sequence. And this is going to correspond to section 7.12 of your textbook. Now, in order to do this, what we're going to do is we're going to focus in on the environment of the continental shelf. So in front of us we have a diagram of the continental margin. Essentially, you can see we've got the continent over here, we have the coastline marked out here by this white line, and then we're on to the continental shelf. And we know the continental shelf is going to be between about 0 and 200 meters water depth. Obviously, once we're past the continental shelf, so that's the slope break, we're going to come down the continental slope, and then we're going to end up down here on the continental rise, which is part of the deep sea floor. But we're going to be focused mostly in this area here. Now, what you'll notice is I've put some coloured bars here, and they show you the areas in which we expect to get certain types of sediment being deposited. So along our coast and essentially underwater closest to the coast, we expect to have sandy sediments. So why do we expect sandy sediments? Well, what happens is we have a lot of action in this region from waves and tides. And this constant water movement is going to mean that fine particles get picked up and transported away. So particles like clays and silts will be picked up by the water and they'll be pulled out into deeper water. This means that sediment that gets left behind is going to be sandy. And so we have a buildup of sandy material in this area because the finer material is being removed. And of course, in most coastal environments, coarser material, gravels, cobbles, boulders, was never present on the beach in the first place. And so over time, we have this area becoming essentially a sandy environment. Now, the silt and clay that was removed from this environment here is going to be pulled out into deeper water, and as the clay and silt bearing water makes it out further away from the coast, the water is going to start to become more and more still. So it's going to become less energetic. Now, because it becomes less energetic, the water essentially is therefore going to have a reduced capacity in terms of being able to transport sediment, and eventually it's going to become so still that the water is actually going to start depositing the clay and the silt. And so once we're out of the sand zone, we go into a region which is dominated by muds. And this is just simply the mud that's been removed from sediment closer to the coast and dragged out into deeper water. Now, as we move through the mud fascies, the mud region, we can, if conditions are right, then enter the carbonate area. So if the conditions are right, so if we have shallow water, warm water, clear water, normal salinity, and we're about 30 degrees north or south of the equator, we have the possibility of forming a carbonate barrier of some kind, like a reef. And if a reef is going to form, it's going to form right out here on the edge of the continental shelf. So why is that? Well, one of the 5 considerations we need in order to optimize carbonate production is clear water. So the water that we have in this region and this region is going to have lots of silt and clay suspended in it, and so it's not really going to be great conditions for the formation of carbonates. However, once we make it out into this region, well, the mud's already been removed. The silt and clay is gone from the water now. And so this means the water that's out here is going to be nice and clear, which is exactly what we want if we're going to think about forming a reef. And so if we can meet the other criteria, then there is the possibility of forming a carbonate barrier out here. So given the right conditions, a continental shelf will have 3 distinct zones: a sandy zone, a muddy zone, and a carbonate zone. The carbonate zone isn't always present. It requires the correct set of conditions to be met. So why is this important to us? Well, when the sea level changes, it causes the position of these areas to move relative to each other. So if the sea level was to rise, it would mean that the sandy region here is going to start moving on land, because remember, if your coastline starts here, then the sea level rises, well, the coastline is now going to be here. And that means that this area here, which was once exposed land, is now underwater. And what region is it going to be in? It's going to be in this sandy zone. Now, as the sandy zone moves inland, that means the mud zone will also move inland, and so will the carbonate zone. And so what you're going to see is you're going to see as sea level changes, it's going to encourage these zones to move relative to one another, and in some cases it's going to make them move over the top of each other. So here's our situation. Here is our coastline. You can see obviously we have our continent here covered in vegetation, we have our beach here, and we have our water here. And you can see that the sandy sediment is continuing from the beach into deeper water, and you can see that layer of sandy material as this kind of white yellow layer right here. So then what's going to happen is we're then going to start to increase the water depth. So we're going to cause the sea level to rise. So as the sea level begins to rise, you can see it shifting position. This is the original position here, and this is the new position. So this is the new coastline. And so this area here, which was once vegetated, has now become a beach. Now, obviously, this means that this area of sandy sediment here is going to move inland with the water, with the coastline. This means that the mud zone, which was further out here, is also going to start moving inland, and you can see it starts to move over the top of the sandy zone, which was there before. Now, as the sea level keeps rising, you will then see here we have the formation of a reef. So now we have the carbonate zone coming over the top of the muddy zone. So by increasing the sea level, we are driving these zones on land, and as the sandy zone moves on land, it pulls the mud zone along with it, and the mud zone pulls the carbonate zone along with it. So as the sea level keeps rising, you can see we have the initial sandy zone gets covered by the muddy zone, and then the muddy zone gets covered by the carbonate zone. So given enough time, you can see that the sea level has continued to move inland even further. So now we're all the way up here. And so by this point, we now have the muddy zone has moved even further inland, and you can see that here. So it initially terminated about there, which is going to be approximately here on the diagram. But as the sea level has been rising, it's continued to move inland. So you can see that as the sea level has been rising, the sandy zone started to move over the top of the continental crust. We then had the muddy zone starts to move over the top of the sandy zone, and the carbonate zone starts to move over the top of the muddy zone. And so this is a relatively straightforward process, and this process is actually referred to as a marine transgression, and it happens a lot in the geologic record. The Earth's sea level is constantly going up and down, and so when the global sea level rises, it's going to cause a transgression. So the sea moves onto the land, and as the sea moves onto the land, it takes these sandy areas, these muddy areas, and these carbonate-rich areas, and it moves the position of those zones relative to each other to the point where the zones start to move over the top of each other, creating different beds of rock. And so we can see the classic sequence associated with marine transgression is a sandstone at the bottom, followed by a mudstone, followed by a limestone. And this essentially is showing us that the water depth is steadily getting deeper. So initially, the water depth out here was relatively shallow. But as the coast moved inland, you can see the water depth gets deeper, and it gets deeper still. And so as the depth of water begins to increase in this area, we can begin to see we have a movement from the sandy environment, which was a relatively shallow water environment, to a muddy environment, which is a kind of intermediate water depth environment, and then eventually into a carbonate environment, which is a deeper water environment still. So the question that you're probably asking is, well, what happens if the reverse happens? What happens if we have a marine regression? And a marine regression is when the sea comes off the land and moves back into the ocean basins. So here's our situation. So our coastline was initially up here. So we have our beach once again, and you can see that we have our distinct zones. So here's our sandy zone, here's our muddy zone, and here is our carbonate zone. But you will notice something has changed. The sea level is now dropping, and this means that the sandy zone will now start to move back out to sea along with the muddy zone and the carbonate zone. So you can see that as the sea level is dropping, as the sandy zone begins to move back into the sea, you can see that it's starting to come over the top of the muddy zone. You can also see that as the sea is moving back out into the ocean basin, the muddy zone has started to come back over the top of the carbonate zone. So as the sea drops back even further, we're going to see this becoming more and more accentuated. So as the sea retreats even more, we can see that the carbonate zone is now being completely covered in this region by the muddy zone, and we can see that the sandy zone is now moving more over the top of the muddy zone. And then if we continue the process, we can see that as the sea levels retreated even further, the zones have continued to move back out into open water. And as mentioned, this process is called a marine regression. And so this is going to produce a reversal in the sequence of rocks that we saw. So at the bottom, we're going to have our limestone. So this is going to represent this layer right here. And then after our limestone, which is this layer right here, we're then going to have a muddy layer, which is going to be represented by the mudstone here. Then on top of the mudstone, we're going to have this sandy layer, which is represented by the sandstone. So this sequence of rocks represents a decrease in sea level. The water is at its deepest when the limestone is being deposited, and then it steadily becomes shallower as we move towards the sandstone. And so you can see how the type of sediment that's being deposited in a specific area is going to change depending on the environment. So as the water depth gets deeper, we move from a sandy environment to a muddy environment and then a carbonate-rich environment. As the water depth gets shallower, we move from a carbonate environment into a muddy environment and then eventually into a sandy environment. So I hope this makes it clear that, this is the kind of basic process that helps to control what we see when we look at our sequence of rock. Essentially, each layer of rock represents an individual environment with its own individual set of conditions. And when we're transitioning from one bed to another, that's exactly what's happening. We are transitioning from one environment of deposition to a new environment of deposition. So the final thing we need to think about is, why do sedimentary layers end? Why does a layer of sediment not carry on forever? Well, the first thing is that every layer of sediment has to have a limit. It can't go on forever. And that's simply because eventually you move so far away from the sediment source that you quite simply run out of sediment. So let's think about a flooding river. So when a river floods, the water exits the river and it covers the surrounding area. And as we know, the water is very, very rich in clay and silt, which is suspended in the floodwater. Well, that floodwater is going to push out over the surrounding area. And so as the floodwater moves further and further away from the river, that means it's had more and more time to deposit the clay and silt which is suspended in the water. And so as the water moves further and further away from the river, it begins to essentially run out of clay and silt because it's depositing it all behind it. And so this means eventually the water is going to run out of clay and silt, and so the layer which is being deposited by that flood will also have to terminate and stop. And so this is referred to as the limit of the environment in question. And now these environments are given a special term which is facies. So when we were talking about the sandy zone, that is going to be referred to as the sandy facies. The muddy zone, the mud facies. The carbonate zone, carbonate facies. And essentially a facies is simply a distinct environment. So as you can see here, we have three distinct facies. We have the sandstone facies here, the mudstone facies here, and the limestone facies here. And we know they're distinct environments of deposition because they're producing different and distinctive rocks. Now, the other option about why a layer of rock terminates, or why a layer of sedimentary rock terminates, is that it comes up against some kind of vertical surface, which means it can't go any further. So in this case, we have ourselves a river, and we can see that we have a river valley. Now, either side of it, you can see that we have a terrace, we have essentially a river valley cliff, and then we have the sediment which is being deposited on the floodplain, which is here in grey. So every time the river floods, it deposits sediment across the floodplain here, but obviously the floodwaters cannot go past the cliff here and the cliff here because the elevation's too high. And so this means that any layer of sediment that's deposited by the floodwaters must terminate against this vertical surface. The layer can't go any further. So once again, sedimentary layers will terminate when they run out of sedimentary material to be deposited. They'll steadily get thinner and then eventually disappear. or a sedimentary layer will terminate when it comes up against some kind of vertical surface that it cannot get past, like a cliff for instance. Okay, thank you for watching everybody, and have a good day.